Okay, so thinking about how you might make a container that holds the most amount of stuff, but has the least amount of packing material. That's sort of like another way that we might use it. Thinking about, let's say you are redoing your backyard or a garden or something like that. And you're thinking about, okay, you don't want to buy that much fencing material, like to sort of enclose your garden, but you want to make sure that it holds the most amount of stuff so that you can put the more plants inside of your garden. Okay, so that's really where we're headed in this section of 4.7 for applied optimization. So we're really thinking, how can we get the most bang for our buck? A lot of times it's sort of tied into money, but how can we make sort of something the biggest it can be while making something else as small as it can be? Okay. And so here's where we're going to start off today. What we know. All right. What we know is that there are things called horizontal tangent lines. And I'm wondering if you can tell me what is true about every horizontal tangent line. All right. So we've got that the slope is 0. Indeed, the slope is 0 of a horizontal tangent line. Okay. And so we're going to take that concept and we're going to apply just that one concept to a bunch of different contexts. Okay. So our context is now, how do we find the maximum or minimum of a desired quantity? All right. So we're looking for the biggest amount or the smallest amount given some parameters. Okay. So let's take a look at the concept behind this. Let's get a picture for maximums and minimums on a graph, okay? So let's say that we have a function sort of, I don't know, like this, like this, okay? So we have some random function. And I realized that on this particular graph that I have this maximum point here, and at that maximum, it actually has a horizontal tangent, okay? So using what Ethan said earlier, the slope here is 0. I could say the same thing down here. And I could say at this point, we have sort of a minimum. And if I were to draw a tangent line that actually touched the curve, then I would have a slope of 0 down here. Okay. This is not unlike, I think it was question number 6 on the exam, where we're thinking, here's a graph and just draw where are the horizontal tangent lines. Okay. All right, questions so far? Okay. So I'm wondering, since we are in a calculus class, if you can connect this idea of slope equals 0 and this function, and think about how can we find these points precisely, right? How do we find the maximum or minimum of a function using calculus. Okay, so that's sort of the question I want us to think about right now. How do we find the maximum or minimum of a function using calculus? All right, so let's take a minute to think about that. And then I'm actually going to have you message me directly with your answer. Okay, so not to everyone in the chat, but just message me directly. What is your answer? How do you think we find the maximum or minimum of a function using calculus? All right, so take a moment, type that into the chat, and then whenever you're ready, send that over to me. We'll kind of see what ideas are floating around out there. All right, I've got a few answers so far. Keep sending them my way. Okay, give folks another 30 seconds to message me if you have not yet. All right. All right, so we've got a really awesome variety of answers here. And so I kind of want to summarize some of the main points that are coming through, okay? So we've had a few folks who said one of two things, okay? Some folks have said, take the, sorry, let me find it again. Take the function and set it equal to 0. So I've seen some folks who said this. I've seen some folks say this, take the derivative and then set that equal to 0. And I've seen some people say this, plug 0 into the function and get a number out. Okay, so there are sort of 3 main answers coming across here. All right, so let's make sure we know they're different answers. All right, option 1, we have f of x equals 0. Option 2, f prime of x equals 0. Option 3, f of x equals, or f of 0 equals a number. So we're just taking 0, we're plugging it into the function, okay? So I'm wondering if we can take a moment to unpack each of these ideas and think about what they're saying. In particular, f of x equals 0. I'm wondering if someone can rephrase that for me. What does that mean in terms of a graph? Okay, f of x equals 0. What does that mean on a graph? Okay, so I'm seeing a few folks who are saying it's the y value of a function. So y value of f of x is 0. Okay. I've heard someone else say that that is the x-intercept. Okay. So we can consider it that, or we can consider it the x-intercept of f of x. Okay. And so I'm wondering if on this graph over here, are the maximum and minimum, do those have a y value of 0? Okay, in other words, this point right here, does it have a y value of 0? No. Okay. What about this point down here? Does that have a y value of 0? No. Okay. Now, you'll notice I've intentionally left out the coordinate axes. What if I drew the axis like this? This is the y-axis. This is the x-axis. Is this point, does this have a y value of 0? Okay, now it does. Does this point have a y value of 0? No. Okay. So one thing I want us to take away from this is when we say f of x equals 0, what we're saying is that the y value of f of x is 0, or that we're looking for the x-intercepts of f of x. And from our picture, we can see that it might be true, but that does not describe both points here. And we want to think about something that can describe what's happening up here as well as what's happening down here. Okay. And so for that reason, saying f of x equals 0 is not going to help us find the max or min. Okay. So not helpful here. All right. Let's take a look at this f prime of x equals 0. So just looking at this, f prime of x equals 0. I'm wondering if someone can tell us, what does that mean? All right, what does f prime of x equals 0 mean? It's symbols, but I want to know what it means in words. Okay. Could say we should modify that statement a tiny bit. So which points is the graph? Graph of what? F of x, f prime of x. Like what are we finding here? Ah, okay. So this middle part, when we see f prime of x equals 0, what we're really saying is when the slope of the original function is 0. Okay. So when the slope of f of x is 0. There's no prime. It's not the slope of f prime. It's the slope of your original function. Okay. So now let's take a look at this picture again to the left. This slope we said was 0. Okay. And then this slope, we said that was 0. When we say f prime of x equals 0, that satisfies both points, the maximum and the minimum. Okay. So this one right here is going to be the one that we think of in terms of how do we find a maximum or minimum of a function using calculus. Okay. Now, because it was brought up, let's talk about f of 0 equals a number. Okay, this is a very common thing that I've seen. People are like, I know there's a 0 somewhere, so I'm just gonna plug it in and get a number and hope that that's correct. Okay, but let's sit and unpack this statement. In words, what does f of 0 equals a number mean? All right, and you can send that to me directly. You can send it into the chat. for everyone to see. Okay, we've got a couple guesses here that this is the y-intercept of, and let's be specific here, it's the y-intercept of f of x since x equals 0. Okay. And so we're also going to say here that this is not how we find our maximum or minimum. It might coincidentally be that, just like f of x equals 0 might coincidentally be that. But the middle one right here, f prime of x equals 0, is really where we're getting the most bang for our buck. Okay. All right. Someone asked a very important question. And that someone said, I mean, f prime of x equals 0. Yeah, that makes sense. But how do we know it's a maximum like the pink one? And how do we know it's a minimum like the blue one? Okay. That is an excellent question. That is an excellent question. How do we know, right? How do we know if the x values of f prime of x equals 0 correspond to a maximum or a minimum? Okay, make that prime a little bit more clear. Okay, so how do we know if the x values of f prime of x correspond to a maximum or minimum? And for right now, my answer is going to be unsatisfactory. I'm going to say, hold on to this question. We will talk about this in 4.3 through 4.5. Okay. Hold on to that thought. We will answer that when we come back from spring break. Okay. For right now, we can assume that the point we find, if the question says a maximum, the point we find is a maximum. And if the question says find a minimum, that the point we find is a minimum. Okay, so for right now, we can assume that when we come back from spring break, that's when we'll address this idea of how do we know the difference between a maximum and a minimum. All right. All right. Let's jot down some useful formulas. All right. And then we will take a look at a problem. So some useful formulas. Let's go with area of a rectangle. Who's got that formula? What is the area of a rectangle? Throw back to geometry. Base times height. Right. Some people call it length times width, but same idea. Okay. What about perimeter of any shape? Okay, so I'm being really specific here. What about the perimeter of any shape? Add it all together. Add what all together? Let's be specific in our language. Add the side lengths together. Okay, so you're going to add side lengths together. Okay. Exactly. You're going to add up all the sides. Okay. Some of these we talked about yesterday, Monday rather. Volume of a cylinder. I'm not sure we actually did. Okay, so volume of a cylinder. Anybody happen to know that equation? Do a quick Google search. I bet you'll find that. There we go. There we go. All right. So pi r squared h. Very nice. All right. What about the volume of a cone? This one I think we did talk about on Monday. Volume of a cone.
Pi r squared times height over 3.
Yeah, so we instead of having just pi r squared h, we have 1/3 pi r squared h. Good. Okay, what about the volume of, let's say, a box? Okay, a box that is specifically not square, but the 3 dimensions are all different.
Base times height times width.
Base times height times width. Great. Okay. And so chance yours would be great if we knew that 2 of the sides were the same, right? Like x and x, like the length and the width were the same. That's not always going to be true if we have a rectangular sort of shape, okay? And so for that reason, we'll go more with like the either length times width times height or base times width times height, okay? Excellent. All right, we're going to get 2 more formulas in here. One of them sort of pairs with the volume of the cylinder. We're going to go with surface area of a cylinder. And that formula, if you were to think about a cylinder, what are sort of the 3 shapes that contribute to a cylinder? We've got circles. Okay, specifically how many circles? 2, exactly, right? Because as Chance said, there's a circle on the top, there's a circle on the bottom, and then that around the side part, weirdly enough, that's a rectangle. Okay, and if you're having a hard time imagining that, you might think about like a soup can, where if you peel the label off the soup can, it unravels into a rectangle. Right? Or if you're not in the business of peeling labels off of cans, if you think about, I don't know, a roll of paper towels or a roll of toilet paper, when you pull a sheet off, it's some sort of square or rectangle, right? And so we have 2 circles, so that's like the top and bottom, plus 1 rectangle, okay? So 2 circles plus 1 rectangle. Now, of course, that's not our formula, but that's sort of where the formula comes from, that we have 2 and the area of a circle, pi r squared, plus 1 times the area of this rectangle. And it turns out that we have this part, which is actually the circumference of the circle, and this part, which is the height. And so the area of that rectangle is 2 pi r h. But that's sort of where those formulas come from. When you look up the surface area for a cylinder, it looks very complicated, but you basically have 2 circles, top and bottom, plus the 1 rectangle. And that's where we get that surface area formula from, okay? Now there's one last thing that I want to put on here, and that is more for the financial side of things. So anybody heard of this word revenue before? I think we might have talked about it at some point, but we heard of that word revenue before? Yeah, when we talked about exponential problems, right? So revenue, when we think about it, is really just a fancy word for saying how much money do you make after all of your costs, right? Because we have our profit, which is like how we have profit, which is sort of like the same idea, that profit is how much you make, but that is really the difference between your income and your cost. All right, so however much money you bring in minus your cost, that gives you your profit, but sort of a fancier word for that, that gives you your revenue. All right, so we've got a bunch of different formulas. Here's what's going to be the same as Monday with these problems. In these problems, we're going to need to be able to identify which one of these formulas we should use. Okay. We will also need to draw a picture. Pictures tend to be helpful. Okay. Here's what's going to be different though. Anybody remember the name of the topic we covered on Monday? What did we cover on Monday? Related rates, okay. And one of our key ideas with is that we were going to have derivatives with respect to time. That things were going to change with respect to time. Today, or anytime we look at these applied optimization problems, they don't tend to involve time. Okay, that's a really important distinction to make in your brain. Related rates deals with time, but optimization instead, what we're really going to see a lot of is words like maximum or minimum. If you see the word maximum or minimum in the problem, it's going to be like 4.7. In contrast, if you see things like find the rate, how does this change over time? Things like that, that's going to be from 4.1. Okay. All right. Let's do a problem, see what happens. Okay, so I'll give you a moment to read through this word problem here. And when you're done reading that, the first thing we're going to do is draw some diagrams. All right. So we have a rectangular garden is to be constructed using a rock wall as one side of a garden and wire fencing for the other three sides. Given 200 feet of wire fencing, determine the dimensions that would require a garden, or that would create a garden of, oh my gosh, maximum area. Then determine the maximum area. Okay. So a few weeks from now, you're looking at a test or something like that, this problem pops up, you see that word maximum, I hope you go back to 4.7 in your notes, not 4.1, right? All because of that word maximum. So I've sort of pre-divided this space into 3 parts. I'm wondering if I can get 3 brave souls to draw some sample diagrams, 1 in each of these boxes. Okay, so use your lovely annotation skills. Let's get 3 diagrams up here and see what happens. All right, we're drawing a picture that represents these the rectangular garden, the fencing, a rock wall. Okay. Those numbers were not in the question, so there should not be numbers on our diagram. But I need some kind of labels on them too, right? Okay, okay. All right. We've got 2 diagrams so far, 3 diagrams. I think there's a text thing that you can type on there too if you feel like it's too hard to write, but these look really excellent. So there's nothing wrong with what's happening here. I love the color coding idea. That is also a great tactic. Okay. All right, so we've got 3 diagrams. In each of the diagrams, there's one side that is the rock wall, and then there are 3 sides that have the wire, okay? So when we're thinking about this, it is unlike a regular rectangle where we have fencing sort of around all 4 sides. Okay, I know the squiggly lines were just to divide the space. I realized that after I drew that. Okay, so we've got these great diagrams here. Now I'm thinking that, you know, when we consider what we might need to label, I'm wondering what might be helpful, okay? And so maybe before we identify what's helpful, I'm just try and squeeze down here some formulas, okay? So, and let's not even put useful formulas. Let's maybe say like formula brain dump. Okay, and let's keep those diagrams up there for a moment. So don't erase anything that you drew, but let's try and get in a formula brain dump. So based on the shapes that we're seeing here, what formulas that we can we think of might be useful for this particular question? All right, you could look back in your notes to the previous page. All right, we've got one that's area of a rectangle. So area of a rectangle equals length times width. Okay, we've got one that is length times width times height. What shape is associated with that? That would be 3D. So I'm not sure that would necessarily apply to this case, right? But I'm gonna go ahead and write it down. And we can sort of cross that off, because I think part of the brain dump is writing out things and then saying, oh yeah, maybe not this one, okay? So area, volume, perimeter, okay? So in this case, how could we write our perimeter? All right, I think David gave a really good definition earlier about what perimeter is. And so I want to think about perimeter for this shape. How could I write that in terms of variables? So let's like not get to the plugging in numbers quite yet, but in terms of variables. All right, so George says 200 equals 2b plus 2h. 2b plus 2h. All right. Oh, 1B, because one side is the wall. Okay, I'm wondering if you could, on any one of these diagrams, tell us what we should label B and what we should label H. Does that make sense? So like, for example, on this diagram, what would we label B and what would we label H? Okay. Okay, so Ethan's got B and then H is on the side. And anyone can annotate on this one. What are our thoughts on what that might be over here in terms of B and H? Or similarly, you could grab this diagram and annotate on that one what the B and what the H is. Okay. I love it. I love it. So we've got base and height, base and height. All right. So if we were to take a look at this one, we've got base and height. Okay. And so in this case, then, if we label it that way, then I think we've really drawn what George said, which is that there's only one base plus two heights to make the perimeter because one of those sides does not need fencing, right? Okay. So let me go ahead and save all these diagrams and then we will move along in the question solving. But I love the diagrams. Love that we're able to connect the notation that we're using in the equation to how we label our diagrams. I think that's really important. All right, so I'm gonna scroll up in just a little bit. So I'll give you a moment to sort of erase your diagram and then think we'll go ahead and move on. All right, so with our formula brain dump, okay, one thing I would encourage you to do in the formula brain dump step is write down any and all of formulas that you think might be useful. And then you can go back in and think about, okay, which ones might be helpful and which ones might not be, all right? And maybe what we can do is go back to the word problem for a second. So as we said on the previous slide, anytime we're looking for a maximum, okay, anytime we're looking for a maximum, we are going to be finding when the slope of the function is 0. Or in other words, procedure-wise, we're doing f prime of x equals 0. So at some point in this problem, I'm going to be taking an equation and finding the derivative. Okay, so at some point in this problem, I better have an equation, I better find the derivative and find the x values that make that work. Okay. Now this right here is the context clue that I think helps us figure out exactly which formula we should be starting with. The maximum area. In other words, I want to find the area graph and I want that to be, I want to find the highest point on the area graph. Okay. Maximum area pulled straight from the problem means that we're going to find the maximum of area. Okay. That means I'm going to find the derivative of area, set it equal to 0, and solve. Okay. So maximum area means find the maximum of the area function. Then in order to do that, we're going to find the derivative of area. We're going to set it equal to 0 and we're going to solve. Okay. That's sort of the big picture. All right, so what do we have for area? Well, we have this area equation. Looks like that might be a good thing to grab. This volume one, we don't want to do this because this is 3D and we only want to think about 2 dimensions, okay? So I've got area equals length times width. Now, based off of how we labeled our diagrams, maybe it's better to call it area equals base times height, yeah? Because we use base and height to label them. Okay, but if you labeled yours with length and width, you could keep L and W. That's totally fine, okay? All right, so length equals base times height. Now, we are in Calc 1, which means we are looking at single variable calculus. Okay. For us, area equals base times height is too many variables because there's area, there's base, and there's height. They're all changing. Okay, so it's too many variables. So in order to sort of maneuver around this, let's try to substitute one of the variables, okay? This means we need a second equation. So we need a second equation that relates base to height. It gives us some sort of relationship between base and height, okay? So let's go back to our formula brain dump. We said area, check. That is the one we want to find the derivative of. Problem though, too many variables, okay? We are going to gloss over the volume one because that's 3D and we want 2 dimensions. But let's take a look at this perimeter formula because we haven't looked at that one yet. All right, so perimeter equals 1 base plus 2 height. Okay, and I think George actually said this, but what is our quote unquote perimeter in this case? Okay, so 200 equals 1 base plus 2 height. Okay, does that make sense to folks where we got 200 equals that? Okay, how much fencing do you have? How much fencing did you buy? You bought 200 feet of it, right? Now you come back to your lovely property and you're building this rectangular garden, you only have 1,200 feet of wire fencing. And that 1,200, that 200 has to go around 1 base and 2 heights, like the 3 sides of the garden.
I think what was confusing for me was that wire fencing was 200 feet, and then it looks like our total is 200.
Yeah, because we have 3 sides that need the fence.
Oh, yes. And then,
yeah, 3 sides that need the fencing. And how much fencing do we have? We don't want any leftover. We only want 200. Or we only have 200, right? So if we're going to use it all, 200 feet will cover the 3 sides that need the fencing. Does that make sense?
So are we only doing this for the 3 sides then? That's why it's b plus 2h, not 2b plus 2h.
Yes, and why are we only doing it for 1b plus 2h?
Because the other base is the wall, the rock wall.
Okay, so we've got 4 sides to a rectangle, but one of those sides is a rock wall, which means we don't have to fence that side. Okay, we're only fencing 3 sides. So we take all the wire fencing we have, which is 200 feet, it's got to go across all 3 sides. Does that help a little bit more? Oh, I appreciate you. Yep, exactly. Okay, so this equation that was in our brain dump, this 200 equals base plus 2h, okay? I'm going to write it down here. So base, or 200 equals base plus 2h, okay? Yeah, no worries. It is the Wednesday before spring break. You are rightfully a little out of it. That is okay. Okay. So I'm wondering with this equation here, if you can answer me this, which letter is easier to solve for? Is it easier to get B by itself, or is it easier to get H by itself? Ah, okay, there we go, right? We still want to find the easiest way to do things. So we could solve for H, but then I'd have to divide by 2. And like the last thing we need right now is fractions, right? So let's go ahead and isolate B. So let's isolate B. And so that means B equals what? What do we get when we isolate B? 200 minus 2h. Beautiful. Okay. So all we did was subtract that 2h to both sides and check out what we have. We have an expression for B. Now this area equals base times height. Our problem was that it had too many variables. But instead of writing B, I can replace it with 200 minus 2h. Okay, so that's what we're going to do right now. Area equals 200 minus 2h times h. How about that? Now we have one variable, which is the comfort zone of Calc 1. Only one variable. Thank goodness. Okay, so once you've got it to have a single variable, that is like big time smiley face, because now we're just using the rules we know to take a derivative. Well, find the derivative, set it equal to 0, and solve. Okay, so that's where we are now. Area equals, let me go ahead and distribute here, 200h minus 2h squared. The derivative of A with respect to h. Take that derivative on the right-hand side. What do we get when we take the derivative of 200h minus 2h squared? All right, so we'll get 200 and then minus not 2h, but 4h. Okay, all right, so we've got our derivative. We got our derivative. What do we do with this derivative? We set it equal to 0. Does that mean we put in a 0 for H? No, please don't put 0 in for H. Then you'd be finding the y-intercept. That's not what we're interested in finding. Okay, so we're going to take this derivative, set it equal to 0. And if this isn't the most straightforward equation we've seen in a really long time, right? So now all we have to do, we have to find out which H value has a derivative of 0, okay? All right, how do we, yeah, it's like you didn't even build it. All right, how do we get H by itself?
Subtract 200 and divide by -4.
All right, so 200 equals 4H, and then H equals 200 over 4, or 50, and we're gonna put units on this, so 50 feet, okay? All right, we've got our height, but the question asks for the dimensions, and then it asks us for the area as well, okay? So the dimensions would be the base and the height, okay? So I've got the height. I'm wondering, how can we find the base? Okay, so take a look at the scribble you have down on your paper. How do we find the base? We know the height. Okay, and specifically, check out this equation that we found, okay? That equation, the one we use to get rid of too many variables, is also the equation that will help us find that variable at the end, okay? So base equals 200 minus 2 times 50, which gives us 100 feet. All right. And then to find area, how do we find our area? Multiply b times h, and that is exactly the equation that we had first in our brain dump. Exactly. Area equals base times height, which gives me 100 times 50. And so I get area equals 5,000. Please do not forget your units, feet squared. Okay. So I will put the diagrams back in when I post the notes, but we started with some diagrams. We did a formula brain dump, and then we thought very carefully about what the question was asking for, connected that to the concept. So find the maximum of area was our concept, and then we connected it to the procedure. Find the derivative, set it equal to 0, solve. Okay. Now, the other problems we look at today will be different scenarios. They might involve any of the formulas we looked at under the useful formulas list. Okay. Kind of like on Monday, we got to be able to decide which formula is going to suit us best in this case. All right. So let's go ahead and take a break. All right. So we've got a few more examples to look at today. Okay. And we're going to go ahead and take a look at example number 2 right now. Okay. So we have that the owners of a car rental company determine that if they charge customers $P per day to rent a car, where P is somewhere between 50 and 200. The number of cars N they rent per day can be modeled by the linear function N of P equals 1000 minus 5P. How much should they charge to maximize their revenue? Okay. So let's take a look. Now this one, I think a diagram isn't terribly useful. All right. So it is something we should consider, but in this particular case, it might not be as useful for us, okay? But I think we can still take the time to make sense of the numbers that we have, okay? So for example, 50 is less than or equal to P, is less than or equal to 200. I'm wondering if we can reframe this in words. Like, what does that mean for this particular context? So what does that mean, folks? We have 50 is less than or equal to P is less than or equal to 200. They rent between 50 and 200 cars per day. Okay, that's one interpretation of that. So this might mean that between 550, between 50 and 200 cars are rented on any given day. All right, any other thoughts on what this 50 to 200 might mean? Customers pay between $50 and $200 a day. Oh, okay. All right. What are our thoughts here? What are our thoughts here? So yeah, Natalia, and maximum number of cars, that might sound like it's more aligned with what Eric set up here. Okay, I think Christina, you bring up a really good point. Let's go back to the word problem for a moment. P dollars. P is in dollars, right? And so since P is in dollars, we might say that we did a sort of a little brain dump about what things meant. But since P is in dollars, I don't think it represents the number of cars, but we could think about it measuring how much a car rental is, okay? All right, let's see what else in here. N of P equals 1000 minus 5P. What does that tell us? The number of cars rented at a certain price the amount of cars rent per day. Okay, so let's see. Number of cars. So number of cars is like the amount of cars that are rented each day. Okay, number of cars that are rented each day. All right. Are there any other thoughts? What are some other thoughts about what N of P might equal, or what N of P might represent is a better way to say that? Okay, well, I've heard students say in the past that maybe N of P represents their income for each day. What are our thoughts on that? Yeah, like revenue or income. Which one do we think gets a smiley face here and which one gets the red X? Right, and again, it might be helpful to look at the units that we have in the problem. Right, the units tell us so much. Income gets the X. Yeah, income gets the X, right? Because it says right here that the number of cars is N. All right, so number of cars that are rented each day, that is indeed what N of P represents, and income each day, well, that's not true based on the units that we see. Okay, so let's think about how we might consider an equation that involves revenue, right? And I'm sort of starting with revenue. Yeah, but sometimes we're reading things and we still will say it means something else, even though the question says it's this, right? So I think it's important to unpack that a little bit, right? And we can feel silly about it later. But when we're looking at revenue, okay, revenue we saw on the earlier slide was income minus our cost, okay? Are there any other equations that maybe we should include in this brain dump, even if we're not going to use them? Anything else that we know that's sort of associated with revenue and cost? Yeah, I can't think of any either. So I think for our brain dump, maybe that's as far as we get for this question. But let's think about what we actually need to do, okay? So this question says maximize revenue, all right? So maximize revenue really means find the maximum on revenue function. And that function could be a graph, it could be an equation, but regardless, we want to find the maximum, okay? And so what is that process? How do we find the maximum? All right, so take a moment, type that process into the chat. You can send it to me via private message if that makes you more comfortable in case you're wrong. That's totally fine. But how do we summarize how to find the maximum on a revenue function? All right, so we want to make sure that this procedure here is something that we feel really confident on, okay? So to do that, I'm seeing folks send me things that look like find the derivative of revenue, set it equal to 0, and solve, okay? And that is precisely what we're going to do. So let's get our revenue equation. So revenue equals income minus cost, okay? Now, what can we use to represent our income? So let's look back at the problem for a moment. What can we use to represent the income? Like how much money do the owners of this car rental place actually make every day? 5p. 5p comes from maybe this equation. Okay, so customers pay, that would be 5 times whatever they pay. How do we know that it's exactly 5 times that? Maybe we need to include this in our brain dump. Income equals 5p. What are some other guesses as to how we could represent that income? Hmm. 1000 minus 5p times p, or 1000 minus n of p. Sorry. P times p. All right, where are we getting that from? Okay, so number of cars that they rented. N of P is the number of cars. I'm wondering why you're subtracting it from 1000. Okay, so why is it 1000 minus N of P? Oh, was that a typo? Because in the chat, it says 1000 minus N of P. I just wanted to.
Sorry, I can't type it. I'm just gonna explain it.
Fine, that's totally fine. Help me out. We want to change that too.
I put the asterisk on the 1000 because right above it I put 100, and that was to correct that. But like, so 1000 is, I assume, how many cars they have on hand. So when N of P equals 0, that's like a good thing. That means they've rented out all 1000 cars. And so I'm subtracting the number of cars they have on hand minus how many cars they actually rented out for that day. And I'll give you like how many's left over.
Ah, okay, okay. I totally see your.
And then you multiply it by how much each car was rented out for, and that should give you.
Okay.
But okay. I don't know what their costs are, so there's also that aspect.
Right. Okay. Okay. Thank you for sharing. So I think that makes a lot more sense where you're getting this from. I wonder though, if maybe it's a little simpler than you think it is. Okay. So what I mean by that is the number of cars that are rented out. Like, you're right in the sense that if they have no more cars left, that means they've rented them all, and that's really good for them. right? But 0, if n of p equals 0, if we put that into sort of like our sentence over here, that means that they didn't rent any cars that day. Does that make sense?
Sorry, if n of p equals 0?
Hmm.
If n, like if p was 0 or n of p equals 0, sorry.
If n of p equals 0, if this side equals 0.
Right, that is true.
No, but I love your thinking because I think that thinking gets us to some of these other responses in the chat. Okay, let's add one more long arrow. So if we know how many cars are rented, okay, if we know how many cars are rented and we multiply that by the cost per car, we will end up with the income, right? So if we know how many cars they rented and how much it cost per car, if we multiply them, then we'll get the income, right? It's almost like you rented 2 cars and each of those cars you rented for $100, then you made $200 by renting that car or those 2 cars, okay? But if you rented 3 cars and each one cost $100, how much money did you make? This is sort of an open question to folks. But if you have 3 cars that you rent out, and each one of those costs $100, how much money do you make renting those 3 cars? Yeah, it's going to be $300, okay? So this right here tells us how much our income is, all right? So as Yitan points out in the chat, N of P is a way for us to see how many cars we rented in terms of how much we charge, all right? And this is actually really important for anyone who's considering like selling something, right? There's sort of a sweet spot in your pricing plan. If you price it too low, yeah, some people might buy it because they think it's a deal, but other people might also not buy it because they think that it's not going to be good quality. Or you sell it for so cheap that you don't make any money, right? So you don't want to lowball the price too much. But let me ask you this, what happens if you set a really high price for something that you're selling? How does that impact the number of people who might actually buy that product? Okay, so like, let's say, I don't know, you were at a bake sale. I don't know if even we're allowed to have those anymore, but let's say we were at a bake sale and you made cookies and you're like, oh, these cookies are $20 for one cookie, right? That's a pretty high price for a cookie. So maybe someone will buy it. Like maybe your best friend will come and be like, oh, I feel really, really bad for you. Nobody's buying your cookies. Let me buy one for $20, right? Yeah, exactly. But on the other hand, let's say that you said, all right, one cookie for 1 cent. I bet you're going to sell out really fast. But I don't know that you're going to make your money back in terms of all the ingredients that you purchased and the time it took to bake all those cookies, right? And so when we think about pricing things, we need to be really strategic about what is the price that will give us the most amount of money, but also give us enough customers, right? So the most amount of money comes from like that balance between income and cost, all right? And so that's what this problem is really about when we're saying like, you could charge anything between $50 and $200, but if you charge $50, you might rent more cars. If you charge $200, you might rent fewer cars. But either way, this function gives us an idea of how many cars you might rent at a specific price, okay? Okay, so now that we've kind of cleared that up a little bit, all right, let's go back to this idea of revenue. So in this case, all right, if we think about our income, we have how many cars are rented, that's N of P, times the cost per car, that's just P. All right, so this is our income. Whoop. In this case, we were not given any information about the cost. And so let's assume that these folks have been around for a while. They own the property, they own the building, they don't really have any costs. So we'll assume that cost is zero. Okay, now this is clearly not the case, but it makes our computations a little bit easier. Okay. So I'm going to go ahead and everywhere I see N of P, I'm going to substitute in 1,000 minus 5P because that's the equation we got for it, and times P. All right. Now this equation is the one that I'm going to try and take the derivative of. This is my revenue equation. All right. Now, lucky for us, in this case, everything is defined in terms of P. I don't need another equation to kind of get rid of a variable because I don't have too many variables, okay? So when we take our derivative, the change in revenue compared to the change in price, let's see, that's 1,000 P minus 5P squared. We take that derivative, we're going to get 1,000 minus 10P. All right, so I'll give you a moment to kind of catch up to that. We have our equation. It had just the right amount of variables, just one on that right-hand side. Then we just took the derivative because of what we said earlier. The derivative of the revenue, if I find where that equals zero, that's going to give me the maximum on the revenue curve. So let's set this equal to 0. We're going to solve for P. So I'm going to add 10P to both sides. I'm going to divide by 10. And it turns out that if I price it so that I'm renting cars at $100 per car, that will be the sweet spot in getting the most number of cars rented out so that I can have the most income.
Can I just kind of rephrase everything we did, and then you can maybe let me know if that makes sense?
Absolutely.
So basically, because we have a negative slope in N of P, that's how many cars we rent out. So the more we charge, the less cars we rent out. But when we consider how much we're making off of each car, which is the income equation, we have an upside down parabola that is within that, you know, we're looking for its vertex sort of, that is between 50 and $200 because that's what we want to charge. So basically on the left side, we're not renting out, sorry, we're not making enough money from each car. We're renting out a lot of cars, but not making enough. And to the right side of it, we're not renting out enough cars because it's too much money. So that where the vertex is the sweet spot between cheap enough that people get it, but expensive enough that we're making the money back.
All right. I'm trying to annotate what you were saying. I think that was a really great way of framing it. If you remember things about types of equations, we've got a negative parabola here, negative something squared, okay? And so our question is really, where is this point? Where is the maximum on that curve, okay? And I think you framed it really well that on this side, it's going to be too expensive for some folks. So not as many people might rent. But on this side, maybe it's too cheap. So you don't make a lot of money, right? And so somewhere in between there, there's this magical moment in time where you make a lot of money because that's what people are willing to pay, and a lot of people are willing to pay for it. Okay. So let's just make sure we answered the question here. It says, how much should they charge to maximize their revenue? And so for each car, if they charge $100, that's when they'll make the most amount of money. Okay. Yes, I agree. I think that was a really wonderful summary. Okay. All right. So that's another flavor of question. Okay. If you're looking to get into business, or even if you think about medicine or any sort of biology, when you're looking at maybe not revenue, but you're looking at how quickly things change, being able to find the maximum amount of things or the minimum amount of things is actually really valuable, right? Like, what is the minimum amount of medicine someone might need for there to be an impact? Or what is the most that we should have of something? Okay. All right, we're going to skip number 3 for right now. We're going to jump to number 4. Okay. Number 4 is also a very classic question. Okay. All right, so example 4. You've been asked to design a 1-liter oil can shaped like a right circular cylinder. What dimensions will use the least amount of material? Okay. And so let's begin with a diagram. All right, let's begin with a diagram. And so we know that we have something in the shape of a right circular cylinder. And all that means is we have a cylinder that maybe looks like this. Okay. And this cylinder, in this particular case, is for a company that wants to package oil. So it's a 1-liter oil can. But the question is, what dimensions will use the least amount of material? So for example, maybe the can looks like this, but maybe the can looks like this. Or maybe the can looks like this. right? If all of these hold 1 liter, which one do you think will use the least amount of material? Right? What are our thoughts? Which one is going to hold or contain the least amount of material? Maybe the last one. Some people are thinking the last one. All right, we've got 2 votes for this one, 1 vote for this one. Any other votes? You don't know about that first and second one. Okay. Trick question. Okay. How many of you drink either soda or like sparkling water? Anybody like a good LaCroix? Wow, tough audience today. Okay. You like apple juice. Okay. Okay. All right. So yeah, actually, David, that's kind of the point, is when we think about like going to the grocery store and buying a can of soda, we typically think that it looks something like this. Okay. The question though is, does that use the least amount of material? Okay. And so let's kind of work through this problem a little bit, and I'll share a story at the end about which ones actually use the least amount of material and maybe why that is, okay? But all right, so we've got this diagram, 3 potential cylinders, but we know that each one of them contains 1 liter of oil, okay? And so let's do a formula brain dump. All right, what formula or formulas might we need to help us with this problem? And again, this is a space to write anything and everything. We might not use it all, but at least we'll have it somewhere, okay? So what's that gonna look like? What formulas come to mind? All right, surface area of a cylinder. Great. That was the 2 circles plus 1 rectangle. Okay. Volume of a cylinder. Pi r squared h. No 1/3 because it's not a cone. Okay. Any other formulas kind of jumping out at us right now? All right. I think we can always come back to this if we need, but let's pick one to be the equation that we will find the maximum or minimum of. Okay. So which one of these equations should we be saying, I want to find the derivative so that I can find the maximum or minimum of this point, of this curve? Okay, volume versus surface area. Volume, how much work we have inside the can, right? The volume of these cans, all 3 of them, have to be 1 liter. So if it's always 1 liter, well, then I don't know that I need to find a maximum or minimum of it, okay? Yeah, surface area. So let's see, surface area. Now, do we want to minimize or maximize the surface area? We want to minimize, okay. So minimize surface area, okay. So that means find the minimum of surface area. To do that, we'll find the derivative of surface area, set it equal to 0, and solve. Exactly. Do we want a really short and fat can? Do we want one that's sort of in between? Do we want a very tall and thin cylinder? Those are all sort of questions we want to answer. Okay. All right. So let's write down that surface area formula. I know that's 2 pi r squared plus 2 pi rh. Let's have a Goldilocks moment here. Does this equation have not enough variables, too many variables, or just the right amount of variables? Yeah, this is too many variables. Okay, too many variables because I have an R, exactly. But oh, cursives, I have an H as well. Too many variables, okay? So because we have too many variables, what we want to think is, how in the world can we get rid of one of those variables, okay? To eliminate one of the variables, we need an equation that relates R and H, okay? All right. Now, before we figure out what this other equation is and actually do the substitution, question for you folks, which one is easier? Do you think it's easier to get rid of the R or the H? All right, we got one vote for the H. H. Okay. Well, if I want to substitute the H, how many places do I have to substitute it in? Just one, right? Just here. But if I were substituting in R, I would have to substitute it in 2 places and I'd have to square one of them. And that sounds like a lot of work, okay? So let's go back to our formula brain dump. We use the surface area, but maybe that volume one will come into play here, okay? Now there's one unit conversion that will actually be very helpful here. And that is 1 liter is equivalent to 1,000 cubic centimeter. Okay, 1 liter is equal to 1,000 cubic centimeter. Now, the reason why this is important is because when we measure things like the radius or the height, okay, we imagine the radius and the height, we're not measuring that in like liters. We're measuring those probably in like centimeters or inches or feet, right? And so because we want to be able to use the units, we got to convert it to something that helps us understand that we're multiplying things to get to that particular volume, okay? All right, so here's what we're going to do. We're going to take the volume equals pi r squared h. What can I include in this formula now? Like, what can I say volume is? Because no matter which one of these I chose, the really short and wide cylinder, sort of the medium one, God bless metric, the really tall and thin one, what is the volume in all 3 of these diagrams? Okay, but 1 liter is not a helpful unit for us. How else do we write it? Yeah, 1,000 cubic centimeters, okay? So I'm gonna say 1,000 equals pi r squared h. All right. Now let me ask you something. In this equation, the 1,000 equals pi r squared h, is it easier to get the h by itself or the r by itself? Okay, I want to get the r by itself. I'm going to have to divide by pi and h, and then I'm going to have to take the square root. I don't know. That seems like too much work. What if I wanted to get the h by itself? How could I get the h by itself? If I divide by h, I don't get h by itself.
Divide by pi r squared.
Yeah, I could divide by pi r squared, right? Then I don't have to worry about a square root. I want to avoid square roots. I know that I'm going to be finding a derivative. And the worst thing I can do for myself is make that equation really hard with square roots, and then I have to get a square root derivative somehow, okay? So we can say that h equals 1,000 divided by pi r squared. And everywhere I see an h, I'm gonna replace it with 1,000 over pi r squared, okay? So it turns out that the thing that was easier to substitute over here was also the thing that was easier to solve for over here. Right? Easy doesn't mean there was no work involved. Easy means that it was better than our other option. Okay. All right, let's make that substitution. Surface area equals 2 pi r squared plus 2 pi r times 1,000 over pi r squared. All right, well, that looks like a gross thing to take a derivative of. I wonder if I should clean that up first. Well, that looks a lot better. How did I get there? Those pi's, they sure do cancel. And one of these r's and one of those r's also reduce. That's how I get 2,000, because 2 times 1,000 gives me 2,000, and then the r is on the bottom. Okay. So I've substituted. I've reduced a little bit, and I'm even going to rewrite it one more time as 2,000 r to the minus 1. And I'm doing that because I know I need to take a derivative. I want to do as much pre-work as I can to make my actual computations go more smoothly. All right, let me pause here for a moment before we take our derivative. How are we feeling about the equation that we got for surface area? Are there any questions about where things are coming from or where things went? So far, so good. Okay. If we need that, I would just be on the lookout for that. So I think there's one of the quiz questions is like 1.5 liters. So that would be equivalent to 1,500 cubic centimeters. I don't think there will be too many other sort of conversions to know, okay? All right, let's take our derivative. The derivative of surface area with respect to the radius. All right, let's see. 2 and pi is a constant, so I can just use the power rule. 4 pi r minus 2000 r to the, what is the power here for r? That second one. That's going to be a -2, okay? Now, some of you, not that many of you, which is good, but some of you, sometimes when we have a power rule, we just forget to actually subtract 1 and we just leave the power off completely, okay? So I would really encourage you to make sure that you remember to do that power rule, okay? Okay, now I've got the derivative. What do I want to do with this derivative? What do I want to do? Yes, we want to set that derivative equal to 0. And if you happen to think, oh, maybe I should plug in 0 for r, I think that Natalia brought up a great point earlier. Plugging in 0 for r would be like you had like a straw, right? You essentially had this picture, but like a really, 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 really tiny radius. So it was like a stick. All right, that doesn't make sense. We don't want such a, we don't know that that's the radius that makes it work, first of all. And second of all, we're going back to the concept that to find the minimum, we need to find the derivative, set it equal to 0 to acknowledge that horizontal tangent, and then solve. Okay. All right, so 0 equals 2, whoops, 4 pi r minus 2000 over r squared. Now I'm going to write it back that way because it makes my life a little easier when I'm trying to solve for r now. Okay. And so I'm going to go ahead. I could do one of two things. I can add the 2000 over r squared to both sides first, or wouldn't life be nice if I could get rid of that fraction? Okay. Either way, we're gonna end up multiplying by r squared. We're multiplying by r squared because that's the denominator that we want to get rid of. So let's see, 0 times r squared is 0. 4 pi r times r squared, that gives us 4 pi r cubed. 2000 over r squared times r squared gives me 2000. Okay, so this idea of getting rid of the denominators to make your life easier is a really important strategy here. Okay, now I think it makes solving the equation a lot easier. How are we going to isolate that r? How?
Add 2000.
Add 2000, all right, so 4 pi r cubed equals 2000.
Yes, and then divide by 4 pi. And then square root. Oh, yes. And then square, no, cube root both sides.
Beautiful. All right, someone throw that in a calculator for me. That is the exact value, but if we were to approximate it to say like 2 decimal points, what would we get? Just so we can start to imagine what this looks like. 5.24. Anybody confirm that? That sounds about right. 5.42, sorry, 5.42. All right. 2 is good enough. I bet it'll be accurate. All right, so we've got our radius about 5.5 centimeter, almost. How am I gonna find h? Because I want to know how tall this can is too. Ah, perfect. So we've got that fancy formula. Okay, now this formula, this one, the one where you used something you knew, you were trying to isolate a certain variable so you could substitute it in, that formula helps with the substitution and it helps you find that same letter at the end of the problem. So 1000 over pi r squared, we substitute our numbers in, our folks getting about 10.84. Okay. All right, so we've got the height of the can. We've got the radius of the can. Is there anything you notice about these two numbers? The radius and the height? It doubles. Oh, okay. What else doubles the radius? The diameter. Oh my gosh. Okay. So check this out. I think this is one of the coolest sort of things that I've encountered in terms of like these optimization problems. Okay. Circle square. Yes, actually, that's really where we're going with this. Okay. Now, I know that not everyone in here is over 21. That happens to be the legal age in our country for consuming adult beverages. Okay, so bear with me for a moment here. But the next time you happen to go to a grocery store, okay, and you look at the adult beverage aisle in the grocery store or like a Walmart or whatever, okay, most of the cans are sort of like soda cans, okay? And in a soda can, it might look like this. And the diameter is actually different than the height. So for a regular, we'll call it regular can, the height does not equal the diameter, okay? Now, if you go through the adult beverage aisle, specifically looking at canned adult beverages, you'll notice that there's one particular brand that looks more like this. So it's a little shorter and a little wider than a regular looking can, okay? In this particular can, the diameter and the height are actually the same. Okay. This can and this can hold the same amount of beverage. Okay, they hold the same amount of beverage. Which one of them uses less material? All right, we've got one vote for the regular one uses more material or less material. Regular. Okay, 2 votes for regular. All right. Let's go back and regular adult beverage. Okay, so let's go back and look at our findings, right? I know we were talking about an oil can, which I would encourage you not to drink the contents of an oil can, but the oil can we knew could sort of come like this, or like this. And so we worked out the problem to figure out what dimensions would give us the least amount of material. And it turns out that the radius being half of the height, well, doesn't that mean that the diameter is the height? Right? The diameter here is 10.84, which is the same as the height. And so it turns out that this process is not just true for a random oil can, but anytime you have a cylinder where you have a top and a bottom and around the sides for the material, if you design your can so that the radius is half of the height, then you will minimize the amount of material you use. So if we revisit these 2 pictures, the one that uses the least amount of material is the one where it is a little bit different shaped than all the other cans.
Is this your favorite icebreaker at the party?
I try not to talk about the math at parties. I feel like then people run away from me. But you can use this at your own parties.
Also, I wanted to add something. So do you by any chance know whether the regular can or the special can beverage is cheaper?
Well, I think sometimes the price depends on the content of the can. But
True.
But if we're looking at just the material, if we assume they're made of the same material and this one uses less material, then the one on the right would be cheaper to make.
Yeah. Well, I just remember because we were talking about this in my engineering class maybe 1 or 2 years ago, and the regular can ends up being cheaper because it actually has more volume than the special can, and then also it's easier to ship because they can store more in less area on the plane, so they can ship more beverages with less area in the plane.
Yes, right. So these are all the other things that we need to consider. Now, I will say, though, in this case, we are assuming they both hold the same amount of volume. So your argument that this one contains more, I think, is not necessarily valid. However, I think you are correct. There's a lot of reasons why, even though this one uses more material, this one is the one that we use typically to store liquids in a cylinder. Part of it too, in addition to maybe being able to stack it better, is if you think about what's comfortable to hold in your hand. If you ever try the beverage that comes in this particular container, it's a little bit weird and awkward to hold in your hand. And so maybe out of comfort, folks actually prefer the one that uses more material. All right, but all of this is to say there is a flow to these problems. And in order to work through the problem, we need to think very carefully about what we're doing, where things can be substituted. And I think that this idea of the brain dump for the formula might be a really good place to start. Like, it's okay if you don't use all those formulas, right? We didn't use the circumference one, but we did use the other 2. And sometimes putting something down on paper helps stop our brain from going down the path of, oh my gosh, I don't even know what to do, right? So like if you write something down, that might just be helpful. All right, so with that being said, I will leave example 3 here for you to try. You can certainly, you know, play around with numbers and see what makes this work, but I would also encourage you to think about how to write equations, that have only one variable so that you're able to use this process of taking a derivative, setting it equal to 0, solving for whatever you're solving for. And I would encourage you to really root yourself in this concept, right? What does it mean to plug in 0 here versus here versus here, all right? And with that, we will stop today's lesson.